Example 1. The number n of bacteria present in a culture at time t in hours obeys the model n of t equals 1000 e to the 0.01 t. So this is an example of bacterial growth, bacteria in a culture. So this is that law of exponential growth. So in this example, we're given our exponential function. So all we need to do is use this function to solve and find different pieces of information. So in part A, they want us to determine the number of bacteria at t equal to 0 hours. Well, if time is 0, no time has passed. So that would be the beginning, the original amount of bacteria. So let's just review that general form of our exponential law. So we have our A of t equals our original amount, a sub 0 times e to the kt. So in our example here, instead of a, we've got n for the number of bacteria. So a sub 0 is the original amount. Well, here, our a sub 0, the number that's being multiplied by e, is 1000. So that is going to be our original amount of bacteria in the culture. So the way this is written, our n sub 0 would be 1000. Another way of looking at it, if we substitute in a 0 for our t, so if we take n of 0, we'll get 1000 times e to the 0.01 times 0. So that would give us 1000 times e to the 0, and we know that anything to the 0 power is just 1, so this would just give us 1000 times 1, which is 1000. But you don't have to plug this in. You can just always know that the number that's being multiplied by the e in that exponential law, in this case it's 1000, that's going to be your original amount. Okay, part B, we want to know the growth rate of the bacteria. How fast is the bacteria growing? Okay, so in our general form of our exponential law, our law of uninhibited growth, our k, the number that's being multiplied by the variable t, is our growth rate. So in our example here, we've got e to the 0.01 t, so that 0.01 is our growth rate. So our k in this problem, so that's our k, which is 0.01, and when we talk about that growth rate, we want to write it as a percent, so we know that's going to be 1%. Now, part C, we want to graph this function using a graphing utility. So we can enter this function into our y equals editor, so we've got the 1000 times e, and then you use your e to the x here, the second function of ln, and you'll enclose your exponent in parentheses, so that's that 0.01x. Now let's talk about our viewing window. So generally, when we're talking about real-life phenomena, we frequently have positive numbers, positive quantities. So in this problem, our t, or our x here, which is our t is time, so we know time can't be negative, so we know time would start at 0, but it's always a good idea to go a little outside the window. So if I started this at 0, my graph wouldn't show the axes, so I'm just going to go a little bit outside. So I really need to show greater than 0. I'm going to go a little bit less than 0 just to give myself a better shape, a better picture of this graph, but you can always, this would be completely okay to put a 0 here. Now my x is time, so again, just play around with the viewing window. So I know my time has to be positive. Again, I'm just going out a little bit outside the window. So I'm going to go up to 200. Again, this is just an example. You don't have to go that high. Since I increased the range of my window, so I'm going from -10 to 200, so I'm going 210 units, I increased the scale from the standard default of 1 to 100. Again, just one example of a correct, useful window. Now the y value in this problem is the n. So that's our number of bacteria in the culture. So again, this can't be negative, but since we're talking about large amounts here with the 1000, we're starting with 1000. I'm going just a little bit outside that positive values. I'm going to go from, instead of 0 and greater than 0, I'm just going to start at -10 just to give myself a little bit better view of the axes. And then we started at 1,000, so you at least want to go past 1,000, and just for example, I chose going up to 5,000. And since I increased that range of values in the y values from -10 to 5,000, that's 5,010 units, I increased my scale from the standard default to 1,000. Again, just one example of a useful viewing window. So I'll go to my graph. So this is why I went a little bit, instead of going from 0 on the x and 0 on the y, I went that -10. That just shows me the axes here a little more clearly. So we can see that increasing ramp shape, and we can see our y-intercept here, and we would expect that to be the 1,000, because when time is 0, there's 1,000 bacteria. We're starting with 1,000 bacteria. So let's make a little sketch in our notes here. So we've got that increasing ramp shape, and we've got that y-intercept of 0, 1,000. So this is our n, and this is our t. Let's clean that up a little bit. And you might want to make a little note of the viewing window. So my x-axis, I went from -10 to 200 with a scale of 100. And on my y-axis, I went from -10 to 5,000 with a scale of 1,000. Again, just one example of a useful viewing window. And then finally, in Part D, we're asked to find the population after 4 hours. So the population, that's the number of bacteria. So we want to solve for n when our t, our time, is 4 hours. So we'll just substitute into our function. We want to find n of 4, the amount of bacteria when the time is 4. So we'll have our 1,000 times e to the 0.01 times 4. So that product, the 0.01 times 4, will be the exponent. So if we enter that into our calculator, we're going to get approximately 1,041 bacteria. So after 4 hours, it will have gone from 1,000 to 1,041 bacteria.